So yeah, so we started here with this one, and again, like I gotta change that up. This one came out of the Lidgdahl book, the one that I had here last time. He has a website actually called Building Thinking Classrooms, and it has links on his site to all sorts of activities like this. There are Facebook groups related to Building Thinking Classrooms at every different grade level you can think about, where they share lots of resources about activities they do, depending on the grade level you're in, depending on the subject that you're dealing with. There's a lot of places too that have resources for like the mild, medium, and spicy questions, where you can have then extension problems for what kids are going to work on as you go through that there too. There was our 4 consecutive integers. So today's agenda, there it is. We're going to go through, talk a little bit about our Mindsets reading that we did out of Bowler. Don't forget that the autobiography, I think, is due technically tonight by midnight. Many people have done them. If it was already done, I believe I already graded all of them that were in, based on the rubric there. There's, in the assignment for this week, there are lots of videos to watch, and then there's a response at the end to it. You'll see that when you get there. Related to, again, lots and lots of math topics are out there. They're just small. Again, those are little mini lessons that are done on YouTube that walk you through the different topics of the domain that we're going to be working on, which is domain 1. And then we're actually going to do the domain 1 worksheet in class. Do not turn it into me. Understand? Don't turn it into me. You're going to work on it. If you finish it, that's great. You are being graded on, am I working? Am I collaborating? Am I figuring things out? Am I finding solutions and being happy where I end with at the end of class? And then you, because you're adults and motivated to learn, you're probably going to take it home and finish it, which is great. You don't have to tell me you finish it. I'm assuming you will finish it, and you'll get your whatever credit, 10 out of 10, 20 out of 20, whatever it is. All right? Again, my goal is, at the end of this class, that you are equipped with being exposed to enough of the mathematics and processes for learning how to do the mathematics that you can teach someone else eventually. Right? And then after you've taught it like 2 or 3 years, you're going to go, oh, now I understand it. My lesson for you on this one is my first teaching job. I was hired at a college prep school, private institution, really high tuition. I didn't think I was going to get the job, but apparently I wowed them in my interview. The interview was a full-day interview where they handed me a book first hour and said, third hour I'm teaching this particular lesson. So I had an hour to map out a lesson plan with activities, not knowing what I had in the classroom for manipulatives, and here's the topic I'm doing. And it was where they were in their book. So depending on what day I showed up would depend on what I had to teach. So taught the class. Got in the interview, I was also asked, what are your favorite maths? And for me, it's always the algebra series up through calculus and beyond. I just love the symmetry of what's going on, how it builds off of itself, going from 1-dimensional to 2-dimensional to 3-dimensional, and then rotations, and I love it. And my least favorite at the time was statistics, mostly because I had one undergrad class in stats. It was calculus-based statistics, which meant we derived every stats formula, and at the very end, very briefly touched on application. And I just really didn't see a lot of fit with that because most of the derivation of stats formulas, they use calculus, but they weren't like flowing from one thing that I could perceive. And then secondarily to stats, my least favorite was geometry. In the first 2 years I taught there, I taught only geometry and statistics. So my recommendation, don't tell them your least favorite, right? But what I learned my first 2 years teaching stats is how much I really do love statistics because I started being able to teach it from an application standpoint, not from a derivation standpoint. But my first year teaching, I know for a fact I taught 2 very key parts of stats wrong. Second year through, I was going through it again. I looked at the book. I'm like, wow, my notes don't make any sense. Looked at the book again and realized, oh, wow, yeah, I taught the previous year this particular topic 100% wrong. And all I could think was, I hope none of them go into statistics. And luckily, none of them did.
Probably because you did it wrong.
It's probably because I did it wrong, exactly. Yes, it's probably because I did it wrong. But it's just like education is an experience and a process, so is teaching. You will not ever be the best teacher your first year. And I usually recommend anytime anybody switches a job, don't expect to really know everything that's going on at the school till maybe year 3. Year one, you are so overwhelmed, drinking through a fire hose, it's a lot going on. Year two, you realize, I didn't even know that happened last year. Are you sure we did that last year? Yes, we did. I was so overwhelmed, I didn't even know what was going on the previous year. Year three, you're like, oh, I can learn to start expecting things, anticipate things, and then maybe start to find a groove so that by year four, you're like, wow, I think I might have a stride in what's going
I'm
on.
year 3 and I don't feel there.
And it's gonna vary by a lot of different people in that realm.
Yeah, because
Yeah.
next year's my 4th year.
Yeah, next year's your fourth year, and you're just not quite. You might get into the fourth year and realize that there might be more that you're remembering than you're giving yourself credit for too.
Mine's my boss.
All right, so there's the math domains. So again, as you're thinking about that lesson plan, which domain do you want to do? Number sense, algebra and functions, measurement and geometry, stats and probability. I'm going to show a video on my other device. So then, the fun stuff. When you start looking at resources online, when we're talking about the different state standards and Common Core standards, when we talk about number sense, what are we really talking about, right? It's just this. And this is what comes up on the State of California website for if you're going to get your multiple subject teacher credentials, you need to understand base 10 place value, number theory, concepts, the order of real numbers, including integers, mixed numbers, rational numbers, irrational numbers. These are all the things that you're required to know. One is the multiplicative identity. All right, that's our education speak for anything times one is itself. That's the multiplicative identity. All right, showing how these can be regrouped and put together and what you will do in that process. Computational tools, procedures, and strategies. Candidates have to demonstrate fluency. So the reason I bring this up is as you're thinking about what's my mini lesson going to include, being familiar with these things eventually. Now, again, this is just an introduction, so I'm not expecting like this great in-depth view. I'm not trying to make this harder than it has to be. You demonstrate fluency in standard algorithms for computing and evaluating the correctness of non-standard algorithms. And you go, what? That's okay. You demonstrate an understanding of the order of operations, rounding numbers, estimating calculations, placing numbers accurately on a number line, etc. So this is 1.1, 1.2, and it just goes on from there. So number sense, what is mathematical fluency? So what does that really mean? It's way more than memorizing facts and procedures. When I learned that history was more than facts and procedures, because that's all I thought it was a long time growing up, it became, there's actually purpose in studying what we're studying as opposed to just memorization of facts and procedures. So to develop fluency, students need to connect their conceptual understanding with strategies, including standard algorithms. This is for all of us that grew up, or now that we've learned it many years ago, we've put it into an algorithm that makes sense for us, right? In ways that make sense for them. I saw some people wrote in their autobiographies that they liked mathematics because there was always a right answer. And I really want to break you of that. There aren't always right answers in mathematics. Sometimes there are many great wrong answers. And sometimes there are no right answers. In land of statistics, where I've spent most of my mathematical career, it's a land of close enough. It's all approximation. We are never definitive about anything, which that statement itself would not be statistical because it was definitive, because it said never. All right, so it's this process of always finding what makes the most sense and does that match with what's going on, not a memorization of facts. I, as an educator, am not a fan of memorizing formulas. Even before the internet, I was never a big fan of memorizing formulas. I had formula sheets. You have to figure out the right formula to use. But there are so many formulas out there that until you study it a long time, you tend to not see the connectedness between all of them and say, the area formula for everything in geometry is really one formula. And you can derive them all from that same place. That takes a lot of time to get there. But once you do that, then you're like, I only need to know the one formula because then it fits for everything that I have in geometry. So having them memorize facts is not going to be super helpful, but knowing, okay, well, which formula would make sense? What procedure would be helpful here? And sometimes there's multiple ways of going about finding that. So what is number sense? So when we talk about the four domains themselves, number sense is form of intuition that students develop about numbers or quantities. Understanding how numbers measure quantities and their change. Number sense reflects a deep understanding of mathematics, but it comes through a mathematical mindset that's focused on making sense of the numbers and quantities. It's kind of like we're defining it with itself, which is not a super helpful way to define a word. So let's look at some examples. When we talk about number sense for what we're expecting, at grade level 3 to 5, they're extending their flexibility with the numbers, understanding the operations of multiplication and division, making sense of operations with fractions and decimals, using number lines as tools. So all very one-dimensional when you're talking about number lines. Then here we start getting into more aspects and seeing them generalized in algebra, so we're getting into 2 dimensions. And then here we're seeing at the high school level parallels, not like parallel lines, but they're seeing the connections between what was going on in these previous years in numbers as it relates to then functions and taking it to that next level. Real and complex number systems, and then also ideally financial literacy, which I think could be started oftentimes down here. And you will see curriculums that do have that in there. So that's a very basic outline of what is number sense, without just saying, well, it's our sense of what numbers are. That's kind of redundant. But what specifically are we working on? So in the number theory aspect, we're talking about the base 10 number system. Everybody's like, oh, it's so great. We got the base 10 number system. And the only problem with the U.S. is that we still use the English system for measurement, which everything else is base 10, but we're not going to have a base 10 measurement system. So we're not metric. Addition and subtraction of intervals, prime and composite numbers. So if it's not prime, it's composite. Factors, multiples, exponents, factorials, positive and negative numbers. All of these things go into number theory. Zero didn't come about. Did you see the number on there? Somewhere like in 640, 650 AD is when zero finally was understood to exist. Before that, it was debated because, well, show me zero. Because everything was counting, right? Show me zero of something. Well, here, what's that zero of? It's anything you want. So does it exist? Does it not exist? And it at first became a placeholder between positives and negatives. You get down to the lowest positive number of 1, and now you're like, oh, now we got to go to -1. But what's between there? Because -1 is odd, positive 1 is odd, and all the other numbers go odd, even, and then going down. So then is 0 even, or is it odd, or is it neither? And it was this, again, it was a theoretical debate. And now it seems like most people are like, well, yeah, 0 is just what's, 2, 1, 0, -1, -2, -3. Like it's just there. It was very debatable for a long time. Getting into divisibility, rational and irrational number systems. Here it is. The base 10 number system or decimal system is an ingenious system. I don't know if you ever think about that. Like it is just crazy how amazing that the system is. It allows us to count and do all that we do without creating a whole bunch of more symbols and more systems. Once you get that one system, like the Gödel's idea of incompleteness, is there an axiom that gets you to the base of everything? The answer is no, but they're still trying. But when we do it, then we only have these symbols that we all need to do. Now, from this, there are other systems that do exist. For those of you that have watched some movies. Matt Damon on Mars. What's the name of the movie? It's just called Mars. Mars, The Martian, right? So they talk about hexadecimal. So they have different sets of ways of counting, which allows for then doing different types of maths. All right, and that it worked best when he was doing how to set up the cameras for doing spelling out words and communicating, because we have a 26 letter based system. So the standard 10 based system didn't work. So he figured out a more efficient way to do it. And then adding in the other, I can't remember, it was punctuation or other things that he added in to his system that worked on a hexadecimal system. I know it's fiction, but still, it's fun. It's math. Cards. Some of you might be familiar with these if you have kids that do Common Core. Some of you go, what is going on? So this is base 10 card. This is a 7 and a 10, and together that makes 17, a 10 and a 7. On the back of the card, it shows the 10 dots and the 7 dots. So when you put them together, 10 and 7 is 17. So getting number sense going with counting versus then what the base 10 cards are going to look like. I do not have these types of cards as a manipulative. If you're thinking, oh, do you have any of those? I do not. And then that gets us to the idea of expanding numbers out. Thinking of this as there's 1 1,000, there's 2 100s, there's 3 10s, there's 4 1s here. And when we're teaching kids number sense and understanding and organizing at the younger ages, this is how we're thinking. We're not necessarily thinking of adding and carrying the 1 and all that kind of stuff going on. I'm going to take that slide out. I don't care. Sorry. Then getting into fractions. I mean, it's important, but I feel like I just hit the same ideas over and over again. One whole amount, getting kids in the process. And I remember doing this and actually setting it up and having kids mark it out into 8 equal pieces. It takes a long time if they have to do that. So giving them a little piece that has all those eighths on there. So you start dealing with eighths. And if I have this same length piece of paper, I can do other fractions. Do fourths. And they'll be able to see that, 2/8 is a fourth. And they can start seeing equalities going on there, even though they might not have the concept of equal denominators for adding and subtracting fractions. And this is a very simple manipulative that you can make on a strip of paper. Mark it with eighths. Take out this line, and now they're fourths. And then we have halves. And then you can talk about thirds and see, well, there is no direct way that you can map up like a third with the eighths. So then how would you go about putting them together for something in the future and setting up common denominators eventually? Open-ended question here for you. See if you can participate, because you've been not talking for a long time and I have been. How is the algorithm of addition related to subtraction? Think, but don't answer. In the same way, too, as you're thinking, you're like, I got that figured out. How is the algorithm for multiplication related to division? Some of you might be saying, what does he mean by algorithm? What is an algorithm? Don't answer out loud. You're just thinking in your head. And if you have to look up numbers or words in your phone, that's what phones are for. Looking up words to see what is algorithm? If I had to explain an algorithm to a kid, what would I say? If I have to explain it to myself, what would I say? So, how is the algorithm for addition related to subtraction? I will take a volunteer. Yes, sir.
You're adding debt or negative numbers?
You are adding debt for negative numbers. Explain more.
So, if I was going to subtract instead of add, I could just add a negative. So, if I have 10 and I want to subtract 5, I could add a negative 5.
So you're adding $5 of debt.
And then I would then lose that $5 to then end up with $5.
And you would lose the $5. I see what you're saying. So going with the dollar value. So if you have $10 and I want to take $5 away, what we're really doing is we're adding $5 of debt to what's going on, which means I no longer have that $5. Mm-hmm. Okay? Anybody else think of it differently? Yes?
I just see it as if it was 7 minus 4 equals 3, I explained to a kid, 4 plus what would equal 7? And
Okay.
Whatever that number
Yeah.
is what 7 minus 4 is.
So if you had, what you're saying is if I had, pick a number here, 7 minus 4 is 3. To think of it as addition, you're saying 3 plus something is 7.
Yeah.
Yes. Yeah. And thinking, so what we're getting at there is then we're also getting at what are referred to as inverse operations. Inverse operations. it's a phrase, no matter what grade level you operate at, I would encourage using that as in terms of math fluency. All right. I would encourage you to avoid, if at all possible, this word. Well, just do the opposite. That has so many different meanings. Do you mean positive versus negative? Do you mean multiply, divide, add, subtract? What do you mean when you say do the opposite? All right. Mathematically specific language would be, what's the inverse of adding? Subtraction. Not the opposite of adding. All right, because they may work in opposition, but they're inversing what's happening, or reversing, if you want to say that too, what's happening. So if you had a good answer for this, you can keep that to yourself, and I go to the next slide. Why does multiplication happen before addition or subtraction in PEMDAS? And I'm also going to do this. If you've not seen it this way, this is one of my gripes about the education system and how a lot of people learned it and then the only way they teach it. Why are these together? And then we'll come back to this question. What are these? Addition and subtraction. And they are what type? Inverse operations. What are these two? Inverse operations, multiply and divide. And then we had E. It's exponents. What's its inverse operation?
Square roots.
Roots and radicals. ER, exponents and roots. So all of a sudden I get all these kids coming into Algebra 1 or Algebra 2, and I say, well, what's the inverse of exponents? They go, I don't know. They all know this. They don't know this. All right. P is just a grouping. All right. But then, really you could sorry. MRDMSA. I mean, it just doesn't flow off your tongue that way. I mean, right? Because these could be switched around. When I'm doing exponents and roots, it doesn't matter the order I do them. When I do multiply and divide, it doesn't matter the order that I do them. Add and subtract, as long as you're subtracting the right thing and we think about it as inverses, it doesn't matter the order that I do them. So 2 minus 3, if I do that as addition, it's negative 3 plus 2. Same answer there. So when I say we can do them in reverse order, it doesn't matter when I really see them as inverse operations. But why do we do multiplication before addition? Does anybody know?
So you could get to the sum that you need to add and subtract?
To get to the sum that we need before we can add and subtract, which is, that's accurate for how we do it, but do we know why we do these before we do these?
Because it's a grouping of additions and subtractions.
And that's a good argument to say it's a grouping of additions and subtractions. So we're saying this is multiple additions, this is multiple subtractions. So then we do the individual additions and subtractions. But the real answer is someone decided.
That's what I thought.
And now we are subject to that decision. So at some point in the axioms that they created, we said we need to have order to how we do it. And it's probable that they said, well, the simplest will be last. This is then a little bit, and then multiple multiplications are exponents. All right? Because if I have 3 times, I'm going to run out of color here. If I go white on white. 3 times 3 times 3, well, that's 3 cubed. So it's an extension up from that. All right. The hard argument against that, well, you can't really say that roots is an extension of multiple divisions. It's not quite the same thing. It's the inverse of multiple multiplications, which are roots. When adding fractions, do I have to have common denominators? Yes.
Have to? If you want to do it right.
If you want to do it correctly, fractions can only be added, legitimately added, when they have the same denominators. Because we're talking about how much of the same whole amount are we taking. And then when we multiply fractions, do we have to have common denominators? No, we do not. You can multiply different things. When you add, they have to be the same thing. So same denominators to add, but multiplying, you can multiply anything. So we talked about this real briefly, the box method, and in terms of how multiplying goes on. Turn off my pen. 20 times 40. So if I'm actually going to be multiplying, this would be multiplying, it's on here. 48 times 26. I have in this box the tens, on this edge, the ones. So I have, I'm using blue there, I have 4 tens, and I have 8 ones. On the left there, we have 2 tens and 6 ones. So when you think about expanding that out, and last time in class, I showed you how that would work with multiplying polynomials. So once students have this idea for multiplying numbers, getting them to a place when they're in algebra and algebra 2, where we're then multiplying polynomials, and we've been doing Common Core long enough, we should get to that place where we show them this method. They go, oh gosh, yeah, this is like how we always did multiplication when we were in elementary school. And then it's a natural progression, because the making sense is I'm finding area. Multiplying is finding area. And when we're teaching it like this, we're really finding the area of each of these rectangles and then adding them together. An area makes sense, like, well, how do I increase the area? So I expand it here, and I have longer side lengths. So then when I finally do 20 and 40, those are easier multiplications to do. That's 800. 6 and 4, that's 24, so 240 to get us to the point of then adding them up. And then the box method for division is similar but different if you've not seen it. So what am I going to be doing here? I'm actually dividing here. Let me just change colors. I'm dividing 792 divided by 3. There's the 7, the 9, and the 2. And the 3 into the 7 is 2 times. That's -6. My remainder is 1. That 1 goes to the next one down, which is the 9, so I have 19. 3 divides into 19 6 times. So that's -18. 3 here because I'm subtracting. 1, my 1 remainder goes to the 2. It's very similar to the algorithm that you learned. It's sort of the box method for how they would do a 3-digit, and it gets more complicated when this is not a single digit. But I wanted just to show how this is for just a single digit. And then you have 12, 3 into 12 is 4 times, so that's -12, and that's 0 for my remainder, so 264. It's similar to the algorithm that we learned, and a lot of us probably rely upon. It is essentially the same thing. They're just setting it up and doing it in a different way so that it's more similar to that box method for multiplying. Oh, I forgot I had this in there. I did not load this one. Let me load that while you take a quick break. Be back in 7 minutes. Types of numbers, back to the actual math portion of our lesson today. Natural numbers, whole numbers, integers. So natural numbers would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So natural numbers. Whole numbers then include 0. And then integers includes negative numbers. So, you could say, well, these are all the positive integers. That's natural numbers. Whole numbers are positive integers and 0. Integers then include, we usually say, whole numbers and negative whole numbers. Rational numbers are any numbers that can be expressed as ratios of integers. Irrational numbers are numbers that cannot be made from a ratio of integers. Irrational numbers, square root of 2. You cannot express the square root of 2 as a ratio of 2 integers. And then you get into a subset of irrational numbers, which isn't in here, but transcendental numbers like pi and e. the exponential. Those are both irrational numbers, but they're special times. And then you have real numbers. So real numbers include all irrationals, all rationals. Well, if it includes all rationals, then that means it includes all integers, whole numbers, natural numbers. And then complex numbers, that's when we get into this. Square root of negative 1. Because here we called all these real numbers, so when we realized that there's more than just real numbers, well, then we called them imaginary numbers. And yes, there's a whole field of study on complex numbers, which later they changed to complex numbers instead of calling them imaginary, because they do exist, just in a different sense and used in different ways. A plus bi is how they're all expressed. So they have a real number or an integer component and then the imaginary number component together to make complex numbers. Rarely, I mean, you'll see some of this appear in passing in Algebra 2. Pre-calc will touch on it briefly. Calculus gets into it just a little bit as well. But then if you really want to study complex numbers, you'll actually do calculus of complex numbers. It utilizes a lot of the exponential. Euler's constant is what it's also sometimes called. All right, and there's my really bad Venn diagram. I blew it up. I was like, that's just terrible. Showing what all the different numbers are. There's my natural numbers. Then the integers include it, so you can see the natural numbers, and then the integers, and then the rational numbers, and the real number system, and they all have little values there. Transcendentals exist out here. All right, so most of what we're always going to deal with are going to be in this range when dealing with K through 12 education. Dabbling slightly into imaginary numbers, but not much. But we do talk about, oh, that's pi I. I don't want pi I. Yeah, those are imaginaries. Pi E out here. When we're talking about factoring, greatest common factor, largest factor, language. 6th or 7th grade math is oftentimes when certain language pieces come out. Factors, terms, RMS. Factors are items that are multiplied and divided. Terms are items that are added and subtracted. Being consistent with our math language when we're talking about what we're dealing with. I see a lot of students forget which ones are which. Factors are multiplied and divided. Terms are added and subtracted. So when we talk about the largest factor, we're talking about the largest number that can be divided. Here we say all the numbers share. So share is a fairly obscure word. I mean, it can mean a lot of different things. So largest factors are largest factor that all the numbers share. Well, all the numbers that can be divided by the same one. That is the largest positive integer that divides evenly into all the numbers with zero remainder. It is found through prime factorization. If you haven't done prime factorization in a while, we pick a number like 82, and you say, what two numbers divide into 82? 2, 41. 2 is prime. Are there two numbers that divide into 41? No, it is also prime. So 82 is equal to 41 times 2, or 2 times 41. Some people will tell you always go increasing order. And that's just, again, it's a convention in mathematics. Is the first one wrong? No. But this is we as mathematicians say this one just looks more appealing. It's like eating spaghetti with your hands. Does it get the job done? Yes. Is it very appealing? No. So we do this instead. Prime factorization. Prime numbers are whole numbers greater than 1 that have only two factors. 1 and the number itself. That's not supposed to be a negative. Two factors, hyphen, 1 and the number itself. That's when my page break happens at the wrong spot. And then I export it and it comes out weird. that was supposed to be here. 1 and the number itself. There are an infinite number of primes, the sieve of Eratosthenes. So Eratosthenes was a mathematician, kind of really seen as a Renaissance man. Rumor has it the guy could, from a standing position, jump over a 6-foot bar. Just jump vertically, right over it. Mathematician, he did a lot in engineering specifically, not really at that time, but I mean engineering type things at the time. Well read, but then he came up with what's called the sieve of Eratosthenes, which was a method for determining primes and prime factorizations long time ago. Don't need to remember that, just, fun historical facts with Mr. Steffen. Least common multiple is the smallest positive integer that is a multiple of both numbers. Just reminding you of some of the language. So greatest common factor, the largest number that they both divide into. And this is the smallest integer that is a multiple of both numbers. So least common multiple, what's the smallest value that both of my values will divide into? Greatest common factor, 2 numbers, what's the largest number that divides out of both of them? Additive identity. It can be added and leaves the value unchanged. What is our additive identity? A plus what equals A? 0. Multiplicative identity. A times what number is A? 1. And yes, I took an entire class called number theory where we proved all of these things. You might say, isn't that pretty easy? It's actually not. Fairly lengthy process. So, what does inverse mean? We've talked about that. What is the additive inverse, the multiplicative inverse? Why do we care about inverses? In mathematics, when we are solving, trying to find items, like we did with the little tiles at the beginning, we did the additive inverse. We subtracted, 6 from each side, and then we found that my 1x equaled 10. So it was 10, 11, 12, 13 for the 4 consecutive integers. All right? So we care about inverses because they help us to, and oftentimes, eliminate things that are in the way of solving a problem. 2 numbers are additive inverses if their sum is 0. 2 numbers are multiplicative inverses if their product is 1. 1/8 times 8 is 1. So 1/8 and 8 are multiplicative inverses. All right. And again, we use that when we're trying to solve equations, looking for unknowns. What does x squared actually mean? X times x. And this is where, if you have been working on developing this number sense of multiplication as area is x times x, which is x squared. It's a square. X cubed x times x times x, which is the area of 1 cube with x as its size. Seeing then that exponents are just repeated multiplications, when we're talking about a to the b, my base, my exponent. Math fluency, learning the language of mathematics, explaining what's going on. Positive exponents, negative exponents, if you recall, x to the negative 1/4 is 1 over x to the 4th. That negative exponents are putting on the other side of the fraction bar. That's like the super simple definition of it. You can get a little bit more into it if you want. X to the 1/2 is the square root of x. If I have x to the 3/5, that would be the 5th root of x cubed. and then all these properties of exponents. Anything to the 0 power is 1. A to the negative n is 1 over a to the n. I just showed that on the last slide. Note, a cannot be 0. If a is 0, here I have 1 over 0. 1 over 0 is undefined. Here, if a is 0, I would have 0 to the 0 power. So then you go, well, what is a to 0 to the 0 power? I mean, could it be 0? Could it be 1? Could it be something else? So again, they just decided we're going to ignore this as even option and just say we're not going to have 0 at all. Just don't do it. Here, if a is 0, we end up with 1 over 0. How many zeros go into 1? If we talk about multiplication and addition, 1 over 0 equals something. If we say 1 over 0 equals x, as multiplication being the inverse of division, what we're also saying is x times 0 is 1. What can x be? Anything times 0 is 0. Anything times 0 is always 0. So this could never be 1. X can't happen. So when we talk about 1 over 0, we say instead that 1 over 0 is undefined. Empty set. Does not exist. DNE. Impossible. Bad things happen. I don't know what happens. The world implodes if we try to divide by 0. All right. I usually say to students, all right, how many zeros can go into 1? All of them. Every 0 that has ever existed will exist. To infinity, they all go into 1. And how much do I have left over? 1. So it also theoretically is equal to infinity, which is also undefined. But that's more of a philosophical debate that we're not going to usually get our. I'll challenge when I got that smarty pants kid who said, "Well, what would happen?" I'm like, "Well, you tell me. You know, find out and tell them that maybe it's infinity, or I send them off on this path. What is 0 to the 0 power? If anything to the 0 power is 1, and 0 times anything is 0, what is 0 to the 0 power? Go." And then they just sit and dwell, and I said, "Don't pull your phone out." Undefined. I'm like, "How do you know it is?" Because my phone tells me. How do you know your phone is right? It's on the internet. It's got to be true. When I have same bases and multiply, I am adding exponents. Same bases and dividing, so a is the base, same bases and dividing, the exponents subtract numerator minus denominator 1, m minus n. Oh, and again, a cannot be 0 because if a is in the denominator, bad things happen. When I have anything being multiplied, raised to the same power, the powers multiply. The power on that a is 1, the power on the b is 1. So it'll be a to the 1 times n, and then b to the 1 times n. If a has a power other than 1, it also multiplies, m times n. Those are rules of exponents. And these can, of course, be worked out and taught, and you walk them through the process and showing how, you know, if I have a to the m, and if I actually just move it into and make it actual, like, values, if I have 3 to the 9th raised to the 3rd, that's the same as 3 to the 9th times 3 to the 9th times 3 to the 9th. That's what to the 3rd power means. Times itself 3 times. And they say, okay, well, now what do? Either I remember this property and add them, 9 plus 9 plus 9 is 27, which is 27, or I write this out really longhand. Well, what is 3 to the 9th? 3 times 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 3. And I do it again. Oh, 3. And then I do it again. How many do I have? I have 27. So what we're really doing is exponents is saving us time. These are cheat codes, kids. Cheat codes, wait. Cheat codes, yes, there are cheat codes to math.
So on that one that says the power of a product property, the way you have
you write it as, like if you had it, if you were, can you do that one with an actual value?
Yes, so if we look at this one with an actual value, if I do, and I'll even do not just to the 1 power, if I do 2 to the cubed, that's a terrible 3, times 5 squared, all raised to the 7th. All right, what that would equal is 2 to the 21st times 5 to the 14th. And then I would be done at that point in terms of simplifying because, now yes, I could go to my calculator and go 2 to the 21st. I go 5 to the 14th. But when they are different bases, they cannot combine.
So you couldn't say that was 10 to.
Correct. I could not say this is 10 to any type of a power.
Okay,
Yeah.
okay, that's what I
Yep.
was thinking.
And we're going to see it more when you get to other parts of algebra where you have, x cubed, y squared, cubed. So this would be x to the 9th, y to the 6th. And they're like x and y are different. This cannot be xy to the any power at all. Yeah. All right. Quick little practice for you here. Give those a try. Let's take a look at these from the top down. If you're not finished, that is okay. So, first thing to remember when looking at the properties of exponents is remembering that the exponent, if there's no parentheses, the exponent is only on what is immediately adjacent to it. Common mistakes here is people will think that this -5 is also to the -2, which it is not. There are no parentheses, which is right when we have our PEMDAS or PEMDAS. If the P is not actually on the exponent, or the exponent isn't on the parentheses, then I'm only dealing with whatever the exponent is immediately adjacent to, and in this case, that exponent is adjacent to the y only. Negative exponent, the property that it was a to the n is equal to 1 over a to the n. So that y will be y squared in the denominator. The -5 does not have an exponent. It stays as -5. The z does not have an exponent. It will stay as z in the numerator. So now we have a negative exponent in the denominator. Two ways to think about this. I could say, well, based on what I just did above it, this will be 4 times 1 over x cubed. Apologize, that's really small. I could have made that bigger. And then, but then that's going to require me to remember that when I divide by a fraction, I multiply by the reciprocal. Which you could do and say, well, then that's going to be 1 over 4 times x cubed over 1. Dividing by a fraction is the same as multiplying by its reciprocal. The reciprocal of 1 over x cubed over 1. Reciprocal, that's another word that we oftentimes hear teachers say it's the opposite. I'm like, no, it's the reciprocal. Because if I'm talking opposite as add and subtract, then opposites can't be multiply and divide. Definitely can't be reciprocal. More arguments for why I don't like the word opposite. Which is then x cubed times 1 in the numerator, 4 times 1 in the denominator. Or it's the recalling that, well, a negative exponent means I just take whatever has the negative exponent and flip it to the other side of the fraction bar. So if I just take this x cubed and put it up here with a positive exponent, then I'm done. It'd be x cubed over 4. So either way, you can get to the same place in that process. Now we have one where we have exponents. The entire thing is to an exponent. What I like to do is say, let's split this up, numerator to the negative third, denominator to the negative third. And then in the numerator, I'll have 2 to the negative 3, x to the negative 3, over 3 to the negative 3. Again, there's multiple ways you could approach this. And then, much like we just did up here, if I just remembered like, oh, I just took that and flopped it up to the top, anything with a negative exponent goes to the opposite side of the fraction bar. This 2 to the negative third flops down here. X to the negative third goes to the denominator. 3 to the negative third goes to the numerator. Yeah, that's it, x. Sorry about that. 3 to the third. All right. But like I said, that's not the only way you could have done. I could have done this and said, well, negative exponent means it gets reciprocal or moved to the, I could say that's 3 over 2x to the third. Also a great way to start. And if I needed to, I could write out 3 over 2x times 3 over 2x times 3 over 2x. So I see that that's going to be 3 to the third over 2 cubed x cubed. And again, you could break it up other ways. Those are just two possibilities. All right. When working on exponents like this, the goal is to get it to a place where I do not have negative exponents, where if I have numbers or values with the same bases, I've assembled them together. 3 is a base, 2 is a base, x is a base. All three are different bases. They cannot be combined. Me personally, I don't care if you convert that to 27 or not. 3 cubed is 27. My goal in having a problem like this is, can you apply the principles of exponents to get it then written as just positive exponents and any same bases are combined together? Once you're done with that, then this to me is complete. Twelve to the 0 is 1. Does the x have an exponent? No, it's just x. Y to the 0 is 1. So I have x. All right. And the last one here, how you do it is a matter of preference for where you start. When I have parentheses raised to powers, I like to get rid of that first. It's just a matter of preference. I like to bring this. So all of these are multiplying. I know that because there's no operation listed, so it's a squared times b to the 4th times c, all raised to the negative 2 power. Powers raised to powers multiply. A to the negative 4th, b to the negative 8, c to the negative 2 times a b squared c squared. The negative means, actually, I'll do it this way first. That a is to the first. They're all bases there. They're all multiplying. When I multiply, I add exponents. A to the negative 4 plus 1 times b to the negative 8 plus 2, negative 8 plus 2, c to the negative 2 plus 2. Yeah, so I have a to the negative third, b to the negative 6, c to the 0, fraction bar. A cubed is in the denominator. That's really small. A cubed is in the denominator. B to the 6th is in the denominator because that's the exponents, the negative exponents. C to the 0 is 1. I could have taken this over here and instead done a to the first, b squared, c squared. That's the numerator. All these are negative. I could have had a to the 4th, b to the 8th, c squared in the denominator. And I could have done it that way. Then I would say, oh, c squared and c squared are identical. They reduce. C squared over c squared is 1. Anything divided by itself is 1. That's how I had the 1, which is also c to the 0. 2 up here, 8 down there, which means there's 6 extra in the denominator. 1 up here, 4 down there, so there's 3 in the denominator. Or 1 minus 4 is negative 3, so that's negative 3. 2 minus 8 is negative 6, or 6 in the denominator. Again, multiple paths forward, depends on where you start as to where it goes. Any questions on that? All right. So what you're going to do now is sitting with partners, by yourself. If you did not print out one, then maybe find someone who did. I printed out one. And you're going to work through
Then I saw that it said in class. I'm like, how am I supposed to do this? In class, I'm like, oh, not supposed to do this by yet.
Not supposed to do it on your own yet. Does anybody need one?
Because you just, like, he's just saying it was under that meant one, to try to figure out what those mean. Like, if he just gave it to you, you know, that representative beginning.
It's 2.24.
Then what did you do here to that to make it first? 4, so 4. So 4 is divisible to 4 and you're 1/3 when you do that. So the next one I do. No.
Two-thirds of the area of pattern.
Okay, so it's not like there's 4 sections to okay, because I was gonna do like. I was like, I don't know how to do this. I have to like do an E3 like you're doing it, so that's 40 thirds and another third. That would be this one is not happening.
2/3 of the area. Oh, yes, yeah, yeah.
Okay,
yeah.
so for this one.
Yes, yes. Making sure I was reading the question correctly. Yes.
Oh, there's 12.
They are the most challenging. Just translating. Here's a question. How to translate the math. Translate the math. Translate the math. Yeah.
Thank you.
Let that cost half. Is it third? Is that
I just moved it, so I was gonna do the 1/3 of the area. I was gonna say.
I did that, I did it the hard way. I knew that I had to multiply by to figure out what it was, so instead of multiplying by extra people, I just made this into a 1/4 by divided by 3, so I divided this into 3, which gave me 4. So 1/4 of a kilometer is equal to 4, so then I multiplied it by 4 to get it.
That's 36.
Alright.
So.
that's one and a half.
Yellow field pattern tile is 2/3 of the area of pattern tile design. Use pattern tiles to make the design. What
You got 16.2, that's what I got, right?
do you have tiles?
No, I don't have tiles. Yeah, not ones that are gonna help with that one.
For all this homework, are we literally uploading each photo?
No.
So if it's one,
How do you do the
line
points?
here.
You're here, you're working on it, you're doing it. I'm walking around, I'll be seeing. You're
Oh,
not gonna upload it.
Okay.
So
that's a lot of paper now.
the yellow
One and a
hexagon
half is also
pattern
equal to
Okay, so that's
two,
two
like
thirds.
one half
Cause it just
plus
says,
one half.
So.
use
Plus
pattern tiles to have.
Right.
Could be, so I added.
That's what it could be.
So this
Yeah.
is
To make.
Yeah, cause if this is 2/3, then that's a third, and that'd be the whole.
so we need to divide this into thirds.
That's
And
right.
then kind of for this one, the same thing, I just basically broke it up into three parts.
Or is it
12
just?
over 16
yeah,
is
so it's
This one I
not-
wasn't
yeah.
sure about.
Yeah, so,
And I don't.
16 out of 16 is equal to 1.
But the thing is, they're saying the whole hexagon is.
Okay.
oh, there, I didn't see that there, yeah, yeah. So then that would be 3 halves, so, oh, yes,
Yeah.
yep.
Just go back.
So then how would I get this?
Yeah.
This is
Another design.
Oh, okay.
So we need
So
to
what if
divide
we don't
that
have
into
another
thirds.
So you just have to add another
So
third,
one
so you would do,
Right,
So
yeah,
10.
so this is 6/10 of something,
Yeah.
what was this?
yeah, we're not gonna add a half, we're gonna add a third. To make it.
No different than saying, well, this was
Even smaller.
2/3 of something, what was the original something, it was this, this, and
But
this.
it's this
There you go,
whole
divide
thing,
into 6.
that's a part of
Or this was 3 halves of something, what was the original something, it was, you know.
The yellow
So,
you know, two sections of that without the other piece there.
Two-thirds, the whole thing is two-thirds.
Corner to corner. Okay, and then you want one third.
Where's the hexagon?
Mhm.
So then that would mean that we should
One
one
third.
Show you that
a
if
half.
you needed to divide
Mhm.
it, if
Just
you
three houses, that would be divided by three.
Yeah, what I
So
would
then you
do,
just add another third of a hexagon to make the pattern, right?
let me see if this will
You're
let
trying
me
to equal to
draw.
two?
Two-thirds equals 2 times 4, which is 3 by 4.
because if this is two-thirds, so then you need one more third is two-thirds.
Yeah, it doesn't let me do that, okay. So here, there,
Or are you trying to go backwards?
there. So this is 3 halves.
So I made it like go up to 2, but you're trying to say it's going back to that. That's a whole pattern.
Yeah.
Okay,
yeah.
so
Now, in here, what I would do instead, think of this. So a regular hexagon are all triangles.
yeah,
This is 3 halves, so this is 3 parts of 2.
okay, so you can take those out.
Yeah, so if I go in here, I get like, oh, it's
Got it.
there.
Okay,
Now that would be what the original. So this was 1. This then becomes 3 halves or 1 1/2.
okay. Okay, perfect.
Yeah.
So you're just trying to go back to 1. I made the 2, okay.
Yeah, 3 halves of what? What was the original? What? What was like this weirdly piece out of it? Yeah.
Okay. So yeah. Actually, it would end up being this, and they take off the last. Because that's 1 1/2, so then we want to try to find 1. You see what I'm saying? So that's 1. And you
So
also have the
let's go
example of
back to
doing,
the
you
area.
want to divide it on each row, you can do this.
Get a hole.
Am I marking the wrong tree, thinking of trying to apply a formula for area when we're looking at this?
Yep.
Because it's the whole thing.
So you take off, because that's 1, and that's 1.
So what was the original? If that's 2/3, what was the original shape?
I mean, it's still correct, but
One of
it's
these.
logistically like that, that's easier to put it in.
She got me used for paper and I can't erase that.
Well, and also, then you get the next one and say, well, now it was
So then we
3
can
halves.
as long as we're.
So now you're saying, well, that hexagon is 3 halves. It's 1 1/2. What was the original? What's the one? If that's 3 halves, 3 halves of 1.
There's our shape.
I'm still hung up on the very first part of it. So the whole thing is two-thirds, so we need something else to make that 3/3.
So in this case, if this is 2/3, think of it as like this. 1, 2. This is 2/3. So that means this is a third.
So it changed shape that we're replicating. And you did the triangle, so you did the opposite of the thing, this could be split up to 3 triangles.
Yeah, so there's, so you get, so the original, you take, so this is 1/3, so you take 3 triangles.
So what's the,
Put it in my original.
it could be anything.
Yes.
It's not like there's one
We-
definitive way.
You said that, we said, yeah, like, you said it wouldn't be equal to 1, 2, 3, 4, 6.
Yeah.
She
So,
said it's still 3
what a
triangles.
lot of people do is that instead of doing this, they said, I'm just gonna take this piece, this piece here, and just like reflect it over,
It does.
which was this, those 3 triangles.
Okay. I just thought you were Don't tell me. Okay. So if this middle here,
You just multiply
that is correct.
one.
So, for diagrams 1 through 5, determine the percent of each diagram that is shaded.
It's 3 halves. So you have 3 halves.
Well, it says percent. Grade is percent as a a fraction, okay, as a fraction of simple form, so yes, as a fraction.
Multiply by 10.
So,
Divide by 10.
the whole thing is one,
Right.
Yeah.
so it can't be 4 3/4. Because that's over one.
8.
It's gonna be less than one, it's a fraction of a whole. So, start by looking and saying, what are the major, breakups that are going on? What are the vertical lines? How are they splitting that up into even chunks?
Divide is 10.
Well, it would be 5 if this one wasn't that.
Alright, so pretend that one's also a 5. So they're each a fifth. Okay, so if you want to think about it, on the top, you have like 1/5. Yeah, that's a fifth, then a fifth, then a fifth, then a fifth, then a fifth, okay. But then the last one was, oh, no, that's broken up. So how much is that narrow left rectangle?
1 is
By your thumb.
One and one fifth. So we have one.
We lose 1.
How much?
This is,
At the end.
Well, if this is a fifth, this is a fifth,
One.
that's a fifth, that's a fifth,
1/3.
how much is that little one? Good.
so we're trying to get to 2. I don't know, I take it as like a half, but it can't be a half.
A half
This
of
is
what?
This is half of 1/5.
Half of a fifth.
Yeah. Multiplied by the rest of the So,
That's 3/5.
Yeah, so half of means multiply, so half times 1/5.
So
and
that's
one
put
three,
that in my calculator.
3/5 of half, but then how much do you take?
3 divided by
How much
5.
do you take off? Cause you have to draw the part, so like, for example, this is 3.
Oh, see, we multiply by the
Do I need to sing
So 110?
110?
110.
I can sing the song, which I'm not going to.
Well, what's the?
Okay,
You were
so
times
this
after.
would be
5/3.
1, so you're just adding it up half, basically.
Yeah,
To
but-
make it 2,
How'd you get the pattern then? What's the pattern?
instead of 1. To get to that whole number, or to
Yeah,
get
like
to
when you, like, so for example, like this, either that way or this way.
So is that
This
half of
this
the
is-
10th?
Yeah, so you can get that. So that is 3 halves.
So 3
Because
over 2
that
is
narrow
1 and a
one, you
half.
said,
So
that narrow one's a
this is
10th.
1 and a half.
Well, then this whole thing is a
So you need
10th.
to get to 1, so
And the
you
yellow
have
bar
to
is half of it.
So that's 1.
So we another, I mean, half of a 10th.
You take out a half of the area. It's like this whole pattern.
No,
That's
that's
1 and a half.
twice of a 10th. Has to be less than a 10th.
basically
It all works, it all works, it's just, it's a weird, it doesn't, it's not how my brain works.
Yeah.
So watching it go through, I'm like,
One more.
that works, but it's correctly wrong. It's how my brain is saying.
I'm a visual person, so I have to see it.
So what you're doing here is yours,
You add
is
those
you're
numbers
multiplying
together.
this as 1.
Or take away the
Yeah.
one
If
piece
this
that's
is
not
1,
shaded. How big is
so
the
you're
one piece that's
multiplying by
not
3
shaded?
halves.
120th.
You
I'm
lose
trying to
area.
see how much is shaded.
Mine was half.
Yeah.
What you're doing is you're multiplying by the rest of
I just
the
wrote times 2, a hexagon, that's what I did, hexagon.
Oh, times up with
So-
like the 1, what does the pattern look like?
So what you're gonna do is you're gonna,
So would it
so let's
be
do it on
the
this one.
area,
This one's a
so
lot easier.
simplify this.
So
So
if
two
this,
times for that is
you
3.
multiply this,
Think in terms of
By
20.
3
2.
fifths of the area.
So you get this one
Six
and
tenths.
another one,
What is,
Right.
what is 1
and then you
equal
divide
to
by
is
3.
20.
So
So
this
is 3/5,
turns
and
into
we're
this,
trying
and
to
multiply by
make
2.
it 5.
No, because this is different, that's a 2/3.
If all parts were shaded, there's
No, no,
20
no.
How would
parts.
you split that up?
Oh, okay.
20 over
This
20.
is two of these.
Yeah, yeah,
You multiply by 2, or,
Would that
no,
be-
sorry. You multiply by 3.
Is 15 too much?
Multiply by 3, so this one, and another one.
I'm getting off.
And then you divide it by 2.
May I use it one more
Take
time?
off
What if I did
half of this, half of it. So you lose a full, and half of this one, you get 1 full
Split
rectangle.
all of them up, so they're all like these little
So
ones.
multiplying by circle. That's what you're doing on all of them.
I just
And
thought
I
that, so
can
if
draw
you
that
just,
down the
So-
middle.
so 3
So-
over 5
No,
times
1,
5
2, 3, 4, 5, 6,
is
7, 8, 9,
15
10.
over 15.
There are 20 pieces.
But how did, what's the pattern look like?
There are 20 pieces. One of them is unchanged.
Right, I'm trying to explain how I'm doing the math.
Not 9.
Yeah.
Or if it would be
No.
easier to just leave it
How
at
I'm
6
explaining.
tenths.
So we're multiplying by the reciprocal, not to the fraction itself.
19.
And divide
We're
it.
multiplying by the
Like, I know you're there, but I'm like, you're saying the wrong number. I know
This
you
is
know what you're
one.
thinking.
Okay, so.
We want
Well, if it's 6
this, we wanna
tenths.
multiply by the
Yeah,
reciprocal.
so that's the whole idea that they
Okay,
did with
so
the,
then
with the
that's 10
multiply, right?
squared.
So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because we're multiplying by 10. And then we're gonna divide 2/3. 0.6 is 2/3.
Yeah.
So 1 and 2/3, so we lose this.
Okay.
And so the ending's gonna be that and that.
But it's not quite 2/3 though, right? It's
0.6,
almost,
6, 6, 6,
if you round up,
is
it'd be
2/3.
0.7, wouldn't it?
So you need 5 of these.
Like
0.6 repeating is 2/3.
0.6 repeating is 2/3.
Yeah. At some point, you have to choose to round, but as soon as you've done that, you.
No longer a third.
Right.
So with that one, you guys saying
Which is funny, because then
Because
0.9999 is all in one.
So which one are we looking at now? This one.
it would be the same thing because there's only that quarter piece.
We can think of the numbers as
What is this
results
up here?
from measuring a unit.
I just drew that in.
Oh, okay, so it's just this here? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many are she? 9 tenths.
Okay, so I wouldn't add that part, even though that's part of the,
Yeah.
alright,
Oh, wait, oh, I see.
because there's.
That is part of it. I thought that was your drawing there. Okay, so
Well,
now.
I drew it in to
Yeah.
make it look like you did,
Got
to
it.
help
So
me.
then then you go like this here, do the same thing. So,
Then it would be 20,
yep.
and then the one left.
But this is the only part shaded. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 are shaded.
Out of the 20. Okay. Okay.
Just do the exact thing they did.
The non-shaded strips.
Take one.
Yes.
So,
Okay.
right, it takes 5.
I guess.
Or
The way that I do math, I think, is more like, I know it in my head.
Mm-hmm.
I'll explain it for like,
how many of strip C
Okay, so
it
there's
takes
5
to
centimeters
make strip
for
B?
B, so 5 of 5 equals 1 for strip A, 1 fifth for strip B.
Mm-hmm.
But like usually it's all equations, why is
That's
it?
because he thinks like equations, like he was doing at the board.
But that's not wrong.
This is right.
So if I, okay,
Okay, so we can.
so I don't have to be showing it through equations? Okay.
7/3.
A lot of this we're talking about conceptually trying to get an understanding of what a fraction is.
Yeah.
Fraction, or equations are beyond
7
this.
is.
Okay.
Yeah, and he might be thinking, how am I gonna be using this doing equations, because that's where he may see himself teaching at that level.
Yeah.
And that's how he thinks that way. So a lot of it is gonna be dictated by like, what age group am I usually working with?
Yeah.
And then how am I gonna use it, how do I explain it, what words do I use?
So it's 2.
Yeah.
Conceptually, it's all the same thing,
1/3.
but we're all approaching it from different
Which would
angles.
be the same
Yeah.
thing.
Okay.
So 3/7 is
Yeah, 5.
Yeah.
I was trying to figure out what is.
So if I take out 1 whole,
So how much extra did you make it be strip A?
you get 10, right?
Oh, okay, 1/5 of strip A.
What's the tiniest?
The, yeah, so if this is 2/3,
D doesn't take 2 strips.
what's the bigger picture? So I'm gonna split this in half, because that's 2.
4 times.
This is a third, this is a third.
we break it into 6.
So if I take another one of these
Mm-hmm.
pieces, and just like, I don't know, reflect it down here,
Okay.
that would be what it was, the original thing. If this is 2/3, so 4,
Oh, 5.
I could go,
Just because there's 5.
Why is 2 fractions?
And then the second one. Lots of extras.
like this. But still, if I say, this is 2/3, that means
It's the same.
those 3,
If 1 is
and then these 3, so this is 1, that's 1.
But that's a half, right?
Well, yeah, but there's 2 parts.
to fill
This is 1, this is here. So like if I wanted to think, I don't have another marker color here, but this part here, just this,
There's 3.
whole thing is a third.
Okay, so 1,
The whole
2,
thing.
3, 4, 5, 6, 7. So how many?
Because the whole thing's 2/3, which means this over here is
Strip C is 3/7.
1/3. Together it's 2/3. But if I have these little lines in here, I'm like, all right, well, actually, this whole thing is a third, which means these 3 together make a third. So I could, instead of, so again, what a lot of people do is we reflect this over here. Oh, that was the original shape, which is 3 triangles.
What's left over?
And they could have been drawn any different places. Yeah, and then the second one is like, this is
Oh, that's why.
three halves.
So that's how many shirts.
So this is three pieces now.
This is.
How do I split that into three pieces?
But it's asking how much of strip three, so strip three is maybe a third. So strip three means one full one, two full ones, or a third.
This and this are all the same.
And
So
then
if this is three halves, then that was the original.
You do get top and
Of strip,
bottom.
to make it
Bottom.
Because this is over one.
The whole shape is three pieces.
That's 1.5.
Front leg, there's one full shape.
Yeah, so this is three halves of, so this is over one, three halves of one. Well, there's two halves. That would have been one. That was another one, so that's three halves. So the half and half and half. So the top number tells you what is, this is split and whatever it is. And then I think the other one was like 6/10. Well, now it's like, all right, this is, those are the 6 pieces. But I needed 10. 1, 2, 3, 4. Ta-da, 6 tenths. Now there's 10 tenths. I mean, you could put those anywhere you want. Right, and that's the beauty of it, is there's a lot of ways to go about it. How do they see it?
It's what Henry did. It's like, do
Right, and again, we're developing a conceptual idea of a fraction.
it's like explaining why they added the dotted
Because
line.
we're way past it.
Honestly, they did all of the work for you. I'm not sure.
Yes. But again, seeing fractions as portions of wholes. The whole doesn't have to be a nice, simple, easy rectangle that we always think of. It can be all sorts of weird shapes.
12, that's as far as I can figure out.
To match up, but then so I did another but we the 18 is only 1/3 of
Yeah,
it.
well,
But
just,
so
yeah.
work out that we're
For participation, parts of the strip below into many parts. Anticipate how the partition is.
Yeah, I just missed a couple. Yeah.
How many parts should you make each?
Sure.
Okay, and this is the process where there's basically to use the teacher wants to go more for the class really now there's like how many
Sure.
is that what you couldn't use something like that without doing
Yeah, it's a little bit different. So this is usually like, we have this, we need to get to there, what do I need to get to there? Here is the, it's, I mean, they're very similar.
yeah, that's what usually if I that's one thing I'm trying to is how I explain that
So
Mhm.
we have 1/3, and this one is 1, 2, 3, 4, 5. This one is
Yeah, it's the, we currently have 6 calculators. We need 15 total for the classroom. How many do I need to divide to?
yeah, so you
Similar, yeah.
okay, it's just the way that okay, just the way that
So that's everything.
Well, and some of that's also realizing like,
So that's the answer.
addition is community.
So
yeah.
what we're looking for is.
So could it be the same question? It could be the same question.
Okay. Okay, so I thought.
If you're gonna make.
If it were subtraction, different story. Subtraction's not community.
Okay.
I got one by 6, these times 6 plus 5 is 11. So it'd be 11 over 6. And I did 4. And 2 plus 1 is 9. 9 over 2 is 7. When I did it together, and the 1, 5, 6 over 4 and a half. Which will give me 11 and 6. So you can break it down to the 9 and 2. But yeah, 4 times 1. I tried to do 1 from over 4 each.
Yeah.
So I started 12, here's you, right, here's 4, 3, 12.
All right, with a couple minutes here left in class, let's take a look at a couple of the ones that you have found most difficult, or if you're like, we haven't even got there yet, but that one looks really, number 12. Some people skip.
Mine.
Okay, what do we got?
This one.
This one? All right, I'm going to,
Well, I was telling her, like, I did it as the top strip is 1/4 of a square. But I don't know if that's right.
Tried not to use any formulas. Okay, so.
so this is what it is. What are we supposed to be doing?
For each square, determine the fraction of the area of the square that is shaded. Explain your reasoning.
All right, determining the fraction of the area that's shaded. So it gets down to that video that we watched on multiplying fractions, finding areas, the wrap, if you will. And much like the other ones, it says, if we assume, so, are these hard? Yes. If you work and struggle and say, I don't get it, come back next time. We will go over it together. So as you kind of work on the rest of this packet.
Thank you.
You're welcome. If you have access to a printer and can easily do it, it's helpful too. If you don't, then no.
I pulled it up on here, but
Yeah.
I didn't know we were.
Well, some people like to work on the actual sheets. Some people are okay just copying it down in their notes. Again, it's a matter of preference.
Turning it in.
Nope, not turning it in. Remember, you're not turning this into me.
Great. So do I email you the answers?
So we don't need to upload it
You
online.
every other middle school.